The first talk is by Yiyun Liu from the University of Pennsylvania about a dependent calculus of indistinguishability.
Hello, everyone. My name is Yiyun, and today I'll be presenting my paper, A Consistent Dependent Calculus of Indistinguishability. It's a collaborative work with my colleague, Jonathan Chen at Penn, and my advisor, Stephanie Weirich. So last year at POPL', I presented DCOI, the dependent calculus of indistinguishability, which is a program language that combines pure type systems and dependency tracking. So instead of using beta equivalence to check the equality for types, we use this new notion of equivalence called indistinguishability for type. This design has several benefits. First of all, it allows us to use the same unified mechanism to support both runtime erasure and proof irrelevance. It also allows us to reason about indistinguishability internally within the type theory. So last year, we managed to show that the DCOI program language is indeed type sound. So while type terms don't get stuck. We used the syntactic methods to show that the language satisfies preservation, progress, and non-interference. And it's all been mechanized in the ROG theorem prover. So type sound is perfect for justifying the use of a DCOI as a program language. However, if you want to use DCOI as a program logic for reasoning, then we also want to make sure that the properties proving in DCOI are actually true. That leads us to the contribution of this year's paper, where we focus on the use of DCOI as a program logic. And we achieved that by first instantiating the axioms and sorts of DCOI with a predicative infinite universe hierarchy to obtain this new language called DCOIω. DCOIω compared to DCOI has some other extensions, including a more powerful elimination form for false and dependent pairs. And we also extended it with infinite inductive type, the natural number type, with the induction principle. And most importantly, we managed to show that DCOIω is indeed logically consistent and also satisfies normalization. And all these have been mechanized in the ROG theorem prover through a logical predicate. So before we dive into the specifics of the DCOIω language, I'll quickly go over the background information about dependency tracking, just to make sure we are all on the same page. So dependency tracking can be thought of as a program analysis that determines how a program is allowed to use its inputs. It has various applications, including security, runtime erasure, and proof irrelevance, and also stage computing. So the applications we'll focus on for DCOI here is runtime erasure and proof irrelevance. Though just to build up some intuition, I'm going to choose an example from security. The underlying principles are the same. So suppose we have this instant messaging software, and in the backend, we have this database which stores the information of the users. So we have publicly available information, the name and the status field, the online status. And we also store the secret information, which is the password of the user. So suppose we have this regular user, Eve, who's trying to access the database. She can freely query all the publicly accessible information, such as whether her friend Alice is online, and the database would happily return the answer. Whereas if she tries to access the password field, then she'll get an access denied error because the dependency tracking system sort of prevents secrets, such as the password, from flowing to a public observer. So dependency tracking is not just about whether the data is secret or public, but it's also about who's accessing it. So if we change the role of the user to the system admin, then the same query would become successful. So in systems with dependency tracking, we sort of like indistinguishability sort of naturally arises as a new way of talking about equivalence. Recall from earlier that Eve was unable to access the password field. So to faithfully picture Eve's point of view of the database, we can blur out the password field. Now, the interesting thing is that suppose we have this other database which shares the exact same name and status field from the original database, but might be distinct on the password field. In this case, even though these two databases might be different from each other, a user like Eve wouldn't be able to tell them apart. And in this case, we say that these two databases are indistinguishable. So the main takeaway here is that indistinguishability, unlike equivalence, is a ternary relation as it also takes into account who the observer is. If we change, of course, the observer from Eve to admin, then these secret information gets revealed, and the two databases become distinguishable. So that sort of concludes the background part of the talk. Though before we move on, I do want to point out that even though this is not a security talk, don't store your password like in a plain text. So the idea we've seen earlier translates very naturally into the design of the DCOI type system. We start off with this very regular typing judgment, and we extend it with this thing called an observer level, which determines which inputs our program is allowed to use. And correspondingly, all the inputs, namely the variables in the typing context, are annotated with their corresponding input levels, such that a variable can only be used when its associated input level is less than or equal to the observer level. So there is some sort of ordering defined for these dependency levels. And for this specific program shown on the screen, we have S, which is secret, as our observer level, meaning that our program can access both the secret and public inputs. So in this case, X plus Y type checks perfectly. On the other hand, if we try to downgrade the observer level from S to P, which is the weaker public observer, then this program becomes ill-typed, because a public observer is not allowed to use the secret input Y, which I represent with the single letter S. So more generally, a system like dependency tracking sort of adds this additional layer of check to, that allows us to specify and enforce the flow of information within our type system. Of course, we can draw these dependency levels from this general lattice structure, though for the rest of the talk, I'm going to be focusing on this very simple two-point lattice that has the public and secret observers. So as we've been seeing earlier, indistinguishability also makes sense in the context of a type system. So suppose we have this arbitrary program A, which is a public computation that takes a secret input X. So from the dependency annotations alone, we can sort of tell that A is not allowed to use X in a relevant way. So if we start off with these two distinct inputs, 3 and 2, and we plug them into this expression A, then the resulting expressions should remain indistinguishable from each other from a public observer's perspective. So this type of reasoning principle associated with indistinguishability is immediately useful for implementing proof irrelevance in our dependency type system. So suppose we have this index function which takes a length index vector and retrieves the element with the mth index from it. So to make sure that this index function is well defined on all inputs, we impose this constraint that m must be strictly less than n, which is the size of the vector, so we avoid the excess out-of-bound error. Now, the important thing here is that this m less than n proof is really intended to keep our function total. Our index function should not inspect how this m less than n proof was created to determine which element to return. And that translates to this property that I'm formally stating over on the slide, which says if we fix the vector xs and we fix the index of the element m that we're trying to retrieve, then it doesn't matter which proof you plug in. You should end up with the same result. So if you're working in a type system that doesn't support proof irrelevance, you're sort of out of luck, because the type signature alone doesn't enforce that the index function can't be defined in such a way that it inspects the proof of m less than n. And instead, you need to do some sort of explicit inductive reasoning unfolding the definition of the index function to prove that this equality indeed holds. Dependency tracking in DCOI allows us to express our intent that this m less than n proof is not meant to be computationally relevant. So we achieve that by first declaring this index function as a public observer through the symbol p. And then we seal this m less than n proof behind a secret input level. So this dependency annotation prevents us from using m less than n, like how the proof is derived to decide which element to return. The only exception being that the secret proof m less than n can be used to eliminate dead branches of the code. For example, when the vector size n is equal to 0, m less than 0 is apparently impossible and allows us to construct false to get an element of A out of nowhere. This kind of usage of this secret m less than n proof in a public context is perfectly fine because that branches of the code never gets executed, so no information gets leaked. So as we can see that the dependency information restricts how we define the index function, though as an immediate reward, our type system now automatically derives that these two expressions, these two index expressions with different proofs are indistinguishable from each other. This is definitionally equal, doesn't require any explicit proof from the user. And in a public computation, you can substitute one term for the other. So if you're already familiar with proof irrelevance, you might wonder, what's the point of adding yet another language to the collection? Well, it turns out, compared to these other languages that support proof irrelevance, DCOI additionally support the use case of runtime erasure, or more specifically, erasable type indices. So earlier, we used this secret annotation to help us do equational reasoning. But we can use the same mechanism to specify which inputs should be erased when we generate executable programs. So here, we annotate the size index n and the type parameter a both as secret to indicate that these are fields that are meant to be erasable. So an optimizing compiler can look at these annotations and generate this erased version of this index function that doesn't even look at the size index, which gives us a more efficient definition. So now we have this type system with all these features, but it wouldn't be very useful if this system turns out to be incorrect. And our criterion for correctness here is formally called logical consistency, which means you can't derive a closed program that has a false type. But intuitively, it just means whatever you prove in this language internally must be true. And we prove this property through this well-known technique called a proof by logical predicate, and where a logical predicate can be thought of as a partial function in this case that maps from a type and a universe level to this set S of lambda terms. So since we're working in a dependently typed language, and DCOI has this feature called large elimination, where you can construct a type by pattern matching over a term. So your type could very well be a blob of computation that is not yet in head form. So that forces us to use this inductive to define our logical predicate inductively. So this inductively defined logical predicate satisfies several important properties. First of all, it's deterministic. So even though we defined it as an inductive relation, it really is a partial function in the sense that if we fix the type A and the universe level I, there should be at most one set S. There should be no ambiguous to the meaning of the type. And furthermore, the logical predicate respects beta equivalence. So if we have two types that are beta equivalent, then they should also share the same meaning. And finally, we have this adequacy property, which says if I have a term that belongs to the interpreted set S, then it should be normalizing. And later, it's going to be useful in the fundamental theorem to derive the normalization and in turn consistency as the corollary. So this kind of proof technique is nothing new. It's already been presented in the past in Martin Loff's notes and also by Kokant through his inductive encoding. Though we did try to streamline this proof a little bit by constructing this baseline proof for dependent type theory in general and build the DCOI specifics on top of it. So what complexity does DCOI bring to this proof? Well, in DCOI, there are types that are not beta equivalent, but are nonetheless convertible through indistinguishability. So one example is the one I'm showing on the screen, where we have this variable f, which is a type constructor that takes a secret input. And as a result, since f can't use its secret, f true and f false are convertible to each other. So as a result, our semantics must account for that, meaning that indistinguishable types must share the same meaning. So without getting into the details, to sort of achieve this, we need to bake some more dependency-related information into our semantics. And we do that by adding this context that maps from variables to their dependency levels. We don't need the full typing information, but we need some information about dependencies. And furthermore, the set S becomes indexed by dependency levels. Once you have the definition of the logical predicate, you can define what it means for an empty, closed term to be semantically well-typed. That's precisely when the type A corresponds to some set in the logical predicate, and the term T belongs to the set indexed at the observer level L. So it's similar to what you would see in a simply typed case, except the ugly syntax to deal with partial functions. So once we have defined semantic typing, we can do the routine exercise of generalizing it to arbitrary context through closing substitution or evaluation. We get to state and prove the fundamental theorem, which shows that syntactic typing implies semantic typing. And normalization and consistency of this language follows as results. And finally, from normalization, we can recover the decision procedure for type conversion, which is really just some form of like normalized. So after you normalize these two types, you can do some kind of syntactic comparison while ignoring the parts that are not observable based on the dependency context. So that sort of concludes the meta-theoretic properties I'm trying to show you today. And here's, I'm only going to flash you the related notes, related work specifically about proof irrelevance, though our paper includes related work about other aspects of DCOI as well, including runtime irrelevance and also logical relations for dependent types in general. That's it for the talk. I'm happy to take questions.
3 minutes for questions.
Hi, Max New, University of Michigan. I didn't understand why your logical relation was partial function and not just a function.
Oh, so, well, for example, you can have some type that is just malformed. Like,
oh, okay, so it's defined over possibly ill-formed types. Okay.
Yeah, so if you're in ACTA, you probably would do something like induction recursion, where everything you're working with is just malformed.
Julia Brakova, Purdue University. So a small question, in your running example with index, you had this annotation, privacy annotation on m less than n, but it didn't include an existential. Is there some sort of limitation on what kind of thing can be hidden, or could you also possibly make the whole existential piece hidden?
Oh yeah, so actually I sort of simplified the example a little. So in practice, in the language, every time you introduce a binder, there's a dependency level associated with it. So I just ignore the dependency level because it's like, in that case, it's like, it wasn't important. But yeah, you can like seal any information behind any level.
Okay, thanks.
Yeah.
Hi, I'm from McGill, Junyoung Zhang. I have a question about your dependency levels. The dependency level have any conditions on the? I mean, what kind of restriction do you have on the dependency levels? Do you have any like?
So I think we so a lattice structure is more than enough. So I think we do require like at least it being a semi-lattice, because we do use that property in our meta theory. Like our consistency proof relies on that. So I know that lattice is more than sufficient, but semi-lattice might be enough.
And may I ask, what's the main difference between this one and the other lattice-like structure? The type theory based on lattice-like mode structure, like granular or the quantitative type theory?
So I guess so the difference is that we don't really do counting here. So it's really like if you can use it, like if your dependency level is like high enough, you can just use something infinitely many times. Like there's no like you can only use it for a certain number of times, that kind of thing. So I think I thought about sort of having a similar type of design, but in a quantitative type system, though I remember running some issues. But I think we should, if you want to talk more about it, we should discuss offline.
right, let's thank the speaker.